Welcome back to new session. In this session, we are going to start induction machine. I request you before seeing induction machine videos, please try to watch transformers topic, then come to induction machine. It will be easy for you to understand. Now, today in this session, so our topic is nothing but induction machine. Can also be called as asynchronous machine, and here we are going to discuss what are the features of induction machine, similarities and dissimilarities with a transformer. What are the similarities of induction machine with transformers? What are the dissimilarities of induction machine with transformers? We'll see. Okay. See, to be frank, we are going to start induction machine or asynchronous machine, or I can say we are going to see three-phase induction machine. In this induction machine also, induction motor topic is very important for us. So please let me keep right here. Let me write three-phase induction motor. Okay. See, induction motor can also be called as asynchronous motor, or I can say induction machine can also be called as asynchronous machine. Because at n equal to ns, I can write here, induction machine can also be called asynchronous machine. The reason is I can write like this: since n equal to ns, at n equal to ns, there is no operation. You may take induction motor, you may take induction generator also. Those machines don't have operation at n equal to ns. That's the reason we can call induction machine as asynchronous machine. To be frank, if n is less than ns, so induction machine operating in motoring mode, I can also call it as induction. It can be used as induction motor. N is greater than ns. Induction machine acts as induction generator. Okay, so please, this is very important. N is less than ns. I'll tell you why n is less than ns in case of induction motor, why n is greater than ns in case of induction generator. We'll see that. So as of now, please try to remember, n is less than ns, induction motoring mode. N is greater than ns, induction generating mode. It's very important. At n equal to ns, we don't have any operation. That's the reason we can call induction machine as asynchronous machine. First, we'll see three-phase induction motor. Here, our topic is what are the features of induction machine. Simultaneously, I'll take what are the similarities of induction machine or induction motor with the transformers. Okay. So let me divide page into two halves: three-phase induction motor, and here I'll take three-phase induction. So first of all, let me take three-phase transformer. Next, I'll take three-phase induction motor. Okay, three-phase transformer, and here let me take three-phase induction motor. Okay, see, first difference. Tell me, what is the principle of transformer? See, first of all, tell me, what is the principle of transformer? Mutual induction. Already we discussed in the transformer topic. So here I can say principle of transformer is I can say mutual induction. In case of three-phase induction motor also, principle I can say that nothing but mutual induction only. Principle I can say mutual induction. So I'm saying, just listen carefully. In transformer, if you give supply to primary winding, okay, so because of time varying current, flux will be produced, time varying flux is produced. tie winding flux links with your primary winding, EMF is induced there. Same flux will go from primary to secondary through transformer core. That's what I can call as I can call it as a mutual induction principle. Here also, if you give supply to stator windings here, so flux will be produced. So EMF will be induced in a stator. Same flux will go from stator to rotor through air gap. So I can say principal mutual induction. Here also I can say principal mutual induction. And next transformer is a single excited device. Transformer is single excited device. Reason also I told clearly in transformer, because by using only one external voltage source which is connected to the primary winding, I am able to induce EMF in a primary winding, I am able to induce EMF in a secondary winding also. By using only one external voltage source, we are able to induce EMFs in the primary winding and secondary winding. That's the reason we can call it as single excited device. Here also, we are giving supply to only to stator winding. So because of the same voltage source, EMF will be induced in stator, EMF will be induced in a rotor also. So it's a single excited device. It is also single excited machine. Next, see, I told you in transformer is a constant frequency device. That means what is the frequency of a primary induced EMF will be same frequency of your secondary induced EMF also. Okay, so let me write here. It is a constant frequency device. What about induction machine or induction motor? It's a variable frequency machine. Because if you take example induction motor, stator frequency will be, example if I take F, your rotor frequency becomes SF, slip times of frequency, that we will see in future. So it's a variable frequency, variable frequency machine. And a transformer is a constant flux device. Okay, I told you already, irrespective of your load changes, you will maintain a core flux constant in a transformer. So similarly, induction motor also, it is also a constant flux machine. So let me write here, it's a constant flux device, and it is also constant flux machine. Okay, constant flux machine. There I will maintain core flux constant irrespective of your load changes. Here we will maintain a resultant flux or air gap flux will maintain constant irrespective of your load changes. Okay. Next, see, I told you in transformer, there between primary winding and secondary winding, you are having core. Core is made up of a magnetic material. So between primary winding and secondary winding, so you are having core. So through that core only your flux is passing. Okay. So I can write, so definitely since core is there, you will be having core losses in case of your transformer. Okay. And I told you already, to manage your transformer core, I need some current. That current also can be called as a magnetizing current, I mu. Okay. So let me write here. Here core contains losses. Okay. Between primary and secondary, so flux is passing through core. Core contains losses. Those losses only can be called as the core losses. In case of induction motor, between stator winding and rotor winding, so your flux will flow through air gap. So air gap does not have any losses. So let me write here. So here air gap exists between stator and rotor, air gap does not have losses. Though air gap does not have losses, here you have to understand some small logic here, because here we are having stator is there, rotor is there. Stator will be having its core. In the stator core only we are placing stator windings. So obviously stator core will be having losses. So therefore let me write here stator core contains losses. Stator core contains losses. Okay, and rotor core losses, I can say rotor core losses are negligible. For that reason I'll tell you, generally core losses or iron losses depends on frequency. You might have seen WH, WE, these two can be called as iron losses or core losses. What is the formula for hysteresis losses? Eta Bmax power X into F into V. And what is the formula for eddy current losses? K Bmax square F square T square. Already we have discussed this one in a transformer. WH equals to eta Bmax power X into F into V. WE equals to K Bmax square F square T square. Here iron loss depends on what? Of frequency. Okay. What is the frequency of your stator in case of induction motor? F. So what is the frequency of your rotor induction motor? SF. SF is very less. That's the reason since frequency is very less, since rotor frequency is very less, I can neglect rotor core losses. Just let me write here rotor core loss negligible since rotor frequency is equals to slip times of frequency. It's very less. That's why we are neglecting rotor core losses. Okay, rotor core losses. And therefore, since rotor core losses are negligible in induction machine, you can take induction machine total iron losses, or you can take total core losses approximately equals to stator core losses. Okay, let me write here total core losses is approximately equals to what? Stator core losses. Okay, right. Next point. See, so 3-phase transformer and 3-phase induction motor. Okay, next point. See, we discussed in the transformer, IW is the current which is used to represent your iron loss or core losses. Okay, so I told you in induction motor, rotor core losses are negligible, but stator core losses are there. That's why IW is used to represent stator core losses. Okay, IW is used to represent. It is used to represent stator core losses. Similarly, induction motor also IW is used to represent core losses, to represent transformer core losses. So I think I had given you value IW is equals to 1 to 2% of full load current. 1 to 2% of full load current. Okay, and at the same time in transformer I told you what is the use of I mu? What is the use of I mu? I mu can also be called what? Magnetizing current. Okay, it is used to magnetize the transformer core. Okay, so I mu value had given you 4 to 5% of full load current, and I naught is the vector sum of I mu and IW. This value also I had given I naught is equals to 5 to 6% of full load current. So please now tell me, what about I mu value, IW value and I naught value in induction motor? Okay, so I mu I told you here 4 to 5% of full load current. Okay, here I mu is equals to 25 to 30% of full load current. I'll tell you reason also why requirement of I mu is more here. I'll tell you reason. 25 to 30% of full load current. And what about IW value? 5 to 6% of full load current. And I naught is equals to 30 to 40% of full load current. 30 to 40% of load current. Okay. Here you may get reason. You may get a doubt. Why I mu required here is less in case of transformer, and why I mu required is more in case of induction motor? Very simple reason. I told you, in transformer, flux is passing from primary winding to secondary winding through core. So core is made up of a magnetic material which is having a low reluctance. You know formula, flux is equals to MMF by reluctance, reluctance proportional to air gap, okay. So here you should understand clearly, it's a very simple thing. In a transformer, flux passes from primary winding to secondary winding through core. Core is made up of magnetic material. In case of induction motor, flux passes from stator winding to rotor winding through air gap. Air having high reluctance. Whenever air gap is there, so reluctance is more. So flux will be less. So to maintain this flux constant, what is the formula for MMF? Number of turns into I mu. I'll require more amount of I mu. Okay. To maintain, so whenever flux is reduced, to increase this flux, so requirement of I mu is very, very large. Very simple reason. Why requirement of I mu is very large in induction motor? Means very simple reason. Since here between stator and rotor air gap is there, air offers high reluctance. Whenever reluctance is more, flux will reduce. To maintain that flux constant, requirement of I mu is very large. I mu is very large. That's why here in induction motor I mu is 25 to 30%. Here I mu is 4 to 5% only. Okay, I can write here. I mu is less. Here I mu is more. What is the reason why I mu is more here? Since air gap exists between windings, between stator winding and rotor winding. And what about I mu is less here? What is the reason? Since so core is made up of magnetic material. Since core is made up of magnetic material, so having a low reluctance, having a low reluctance. That's the reason I mu required is less. And very simple reason. Once again, I'm just saying, we discussed in transformer. Whenever requirement of I mu is more, your power factor will reduce. Okay. So let me write here some more differences here. 3-phase transformer and 3-phase induction motor. Since requirement of I mu is more in induction motor, what about power factor is very less. Okay. So here power factor is less. Here power factor is more. So let me write that power factor value also. No load power factor is approximately equals to, here I am saying 0.2 lakh. We already discussed in transformer. Please try to refer the topic. No load power factor is 0.2 lakh. And here no load power factor is approximately 0.1 lakh. 0.1 lakh. Okay. So in addition to this, so many points are there. First of all, note down up to this. Yes. See, next, tell me in case of transformer, flux is time varying or space varying. So I told you already, in a transformer, we are giving time variant source to the primary winding. So current taken by the transformer is time varying nature. Flux produced in the transformer core is time varying nature only, not space varying nature. So let me write here. Here flux is only time varying. Flux is only time varying. Whereas in case of induction motor, flux is time varying, and space varying. If a magnetic field or if a flux is time varying and space varying, what is the meaning for that? That is, magnetic field is rotating. That is, rotating magnetic field is produced. We'll discuss how rotating magnetic field is produced in a three-phase induction motor in future. So as of now, flux is time varying and space varying. That is rotating magnetic field, RMF. Rotating magnetic field is produced here. See, we'll discuss in future what are the conditions for producing rotating magnetic field means. The three-phase current should be time displaced by 120 electrical, and windings, three-phase windings should be physical displaced by 120 electrical. But in case of transformer, currents are displaced by 120 electrical, that is okay. But windings are not physical displaced 120 electrical. Their flux is only time varying nature. It is not space varying nature. That's the reason, therefore, rotating magnetic field is not possible in a three-phase transformer. But in three-phase induction motor, yes, rotating magnetic field is produced. Next, tell me, can I call transformer as energy conversion device, which we discussed already in the transformer starting topic. See, internally, I can call transformer as a energy conversion device because we are giving electrical energy to the transformer. It converts into magnetic energy. Once again, means nothing but core flux. Okay, electrical to magnetic flux. Once again, from flux 2, you'll be having a EMF will be induced in the secondary winding. So transformer is an energy conversion device internal because electrical energy is converted into magnetic energy. Magnetic energy is converted into once again electrical energy. But externally, we cannot call transformer as an energy conversion device because input is electrical as well as output is also electrical. Transformer is not energy conversion device externally. But what about induction motor? We are giving input energy, which energy? Electrical energy. What about output energy? Mechanical energy. So it converts electrical to mechanical. That's why it's an energy conversion device, energy conversion machine. To be frank, induction machine is a electromechanical energy conversion machine. So let me write here. Externally, transformer is not energy conversion device. Let me write in short form ECD, energy conversion device. But three-phase induction machine is a energy conversion machine, because it is converting. If you take example induction motor, which converts electrical to mechanical. If we take induction generator, it converts mechanical to electrical. Therefore, induction machine is a electromechanical energy conversion machine. So a transformer is a not energy conversion device externally, but induction motor is a energy conversion machine. Okay, please note down. Next, if you see, in transformer, whatever primary winding is there, that primary winding is just like analogous to stator in induction motor. In transformer, whatever secondary winding is there, it's just like analogous, I can say, rotor part and induction motor. Okay, so let me ask a simple question here. In induction motor, can I keep keep rotor open? No, because see, induction motor means you have to produce torque has to be produced there. So whenever rotor is closed, then only some current will flow in the rotor. Because of that, rotor flux will come. Because of rotor flux, torque will produce. Okay, so definitely rotor should be here blindly short circuited. Without rotor short circuited, there is no current flowing in rotor, there is no flux concept, there is no torque will not be produced here. Therefore, definitely rotor should be short circuited here. Okay, short circuit here. Can I short circuit your secondary winding here? So to be frank, you should not, secondary winding should never short circuit. Because if you short circuit secondary winding, and where can you apply load? Okay, you may think that during SC test we will short circuit secondary winding. That is different case for finding your full load copper losses. I am asking generally, can you short circuit secondary winding? No. But here rotor should be short circuited. Okay, let me write here, in case of a transformer, secondary winding should not short circuit. Here rotor should be I can say rotor should be blindly short circuited. Short circuited. Why? Then only torque can be produced. So rotor should be blindly short circuited for production of torque. For production of torque, I can say. For production of torque. Okay. Now tell me, in case of a transformer, since it is a static device, I don't have any mechanical losses. But in induction motor, mechanical losses will be there. Okay, let me write here, in case of transformer, mechanical losses, nothing but friction, windage losses. Are, I can say, absent here. Whereas in case of induction motor, yes, I can say that friction, mechanical losses are present. Mechanical losses are present. Okay, please note on this one also. Right. Next, if you see, so these are the, I can say, points, similarities and dissimilarities of a transformer and induction motor. Now please let me see, in case of induction, in case of motor family, so you are having generally induction motor is there, synchronous motor is there, DC motor is there. Okay, in case of motor family, I can say that induction motor is very famous. Okay, see, before invention of power electronic devices which are used to control the speed of induction motor, DC motors were famous before invention of power electronic devices. Okay, so because in DC motor, by using armature resistance control method, field control method. Okay, we are able to control the speed of your DC motors. Okay, but here after invention of power electronic devices, in case of your induction motor also, so during these days I can say that induction motor is very famous because of invention of a power electronic device. Okay, and see here I can write here as a note here, note, before invention of power electronic devices, speed control of induction motor was difficult. Therefore, DC motors were famous before invention of I can say power electronic devices. Okay, but see guys, after invention of power electronic devices, okay, speed control of induction motor is effective. At the same time, maintenance will be less in case of induction motor. In case of DC motor, you have to replace brushes frequently, you have to replace brushes, and you have to clean commutator segments frequently. So that maintenance will be less in case of your induction motor. Because of these reasons, I can say that after invention of power electronic devices, speed control of induction motor is effective. I can say, yeah, induction motors are famous. I can say nowadays induction motors are famous. To be frank, in 90% applications, we are using induction motors are used. Induction motors are used. And here one thing you have to understand, you have to remember this as a note. See, DC shunt motor, if you see, observe DC shunt motor, so almost all speed will be constant from no load to full load in case of DC shunt motor. So definitely speed will, from no load to full load, if your load increases, so drop will be there, speed will reduce, no doubt, but the drop is not that much. So DC shunt motor can be called as constant speed motor, since your speed is almost all same from no load to full load. So in case of induction motor also, induction motor is having shunt type characteristics. Just like it is a speed point of view, I can say that whatever I said in case of DC shunt motor, speed is constant from no load to full load. So in case of induction motor also, we can say speed will be almost all constant from no load to full load. That's why we can call DC shunt motor, induction motor will be having shunt type characteristics. Let me write that point here. Induction motor has shunt type characteristics. Okay, that is it can be used as constant speed motor. And okay, and you have to understand a small thing here, because I told you in case of induction motor, mechanical loss will be there. I told you already, mechanical losses will be there in induction motor. Mechanical loss is nothing but you will be having friction losses and windage losses. In this friction loss also, we are having two classifications are there. Okay, here having bearing friction losses, and brush friction losses. Okay, here bearing friction loss proportional to speed of motor, brush friction loss proportional to speed square of motor, windage is proportional to speed cube. This you have to remember. That means indirectly I can say that mechanical loss depends on what speed of the motor. So I told you here, induction motor, it can be used as constant speed motor because speed, there is a negligible change in speed from no load to full load. That's the reason whenever speed is almost the same from no load to full load, can I take mechanical loss as constant loss in case of induction motor? Yes. So that's the reason. Let me write here. Note one second here. In induction motor, mechanical losses can be taken as approximately constant. Mechanical loss can be taken as approximately constant. Since there is negligible change in speed, from no load to full load. That's the reason the losses which are depending on your speed can be taken as almost all constant in case of your induction machine. Okay, please note on this. Yes. Next, see, I told you here, you have to remember this point here. In motor family, I can say induction motors are famous. That you have to remember. And let me tell now, in a generator family, during these days, which one is very famous? We'll see. See, in generator family, I can say that which one is very famous nowadays means obviously you are using alternator. Alternator can also be called as synchronous generator. So why induction generator is not that much famous as alternator means? Let me write here induction. Can say generator. What is the other name for this? Asynchronous generator. Asynchronous generator. So very simple. I can write here. Alternator can also be called as a synchronous generator. So that means what? What is the speed of your rotor? Speed of your rotor in case of your alternator. Since it is synchronous generator, it always has to run at n equal to ns. Here, if your rotor is running at n equal to ns, I already told you that we don't have any operation. So in case of induction generator, speed will be greater than ns. N is greater than ns here. Okay. So to be frank here, we are using always rotor has to run at n equal to ns only. That means prime mover. Prime mover is the one which gives mechanical energy to this generator. So we are using constant speed prime movers are used here. Constant speed prime movers are used here. What about here? I am using here variable speed prime movers are used here. Prime mover is the one which drives this generator, which gives mechanical energy to this generator. Okay, we are using here constant speed prime movers are used here, and here variable speed prime movers are used. Okay, and one more thing, in case of alternator, we are having a speed governing mechanism is present. Speed governing mechanism is present. Thereby it will maintain speed always constant, that is n equal to ns. It will maintain always n equal to ns. Here I can say no speed governing mechanism. Okay, and see guys, you just remember these points, and let me have some two notes here. Let me write two notes, 2 points here. First point. See, since the alternator is always running at n equal to ns, since the alternator is always running at n equal to ns, you know formula for frequency f is equals to np by 120. np by 120. N means speed, p means number of poles. Okay, 120. So here, if n is always n equal to ns, so obviously frequency will be constant. That means if you take alternator, so whatever EMF induced in that alternator will be having always frequency f. Let me take example 50Hz. Always frequency 50Hz will be there. That means if there is because of using speed governing mechanism, it will maintain the speed constant. It will maintain always at n equal to ns. So frequency will be always constant. Whenever frequency is constant, you can directly connect supply coming from alternator to the grid directly, because your grid frequency is 50Hz. You can connect this output of your alternator to directly grid. So there is no change in frequency, you can directly connect this supply to the grid. But in case of induction generator, since n is greater than s and I don't have any no speed governing mechanism, so if n is greater than s, so obviously frequency you will get other than 50Hz. Other than 50Hz supply you will get. But grid frequency is always 50Hz. That means this whatever frequency other than 50Hz is there, that has to be converted to zero frequency. From 0 to 1 second required frequency 50Hz. So for this I need some interfacing medium. What is the interfacing medium? In induction generator, okay, induction generator, so AC to DC to AC, interfacing medium is required. Interfacing medium is required for connecting supply of induction generator to grid. That means you will get some other frequency here which is not equal to, which is not equal to 50Hz. You will get here some other 50 frequency will get here. So that other than 50Hz has to be converted to zero frequency, AC to DC. Next, 0 to DC has to be converted to AC. That means here I need 0 to 50Hz supply has to be converted. Means here frequency has to change from AC to DC to AC. That means I need AC to DC to AC interfacing medium is required for connecting supply of induction generator to grid. But in case of alternator, since n is always equals to ns, so we'll get frequency 50Hz only. Obviously, we can directly connect the supply of alternator to grid. I don't want any interfacing medium there. So let me write here. In alternator, supply is directly connected to grid. That means what? That is interfacing medium is required or not required? Not required. Interfacing medium is not required. So therefore, if you see all those things, so obviously when compared with your induction generator, okay, alternator is very famous. Okay, so let me write here. Therefore, alternator is used widely in, I can say, generator family. Generally, alternator is used widely in generator family. So this when compared to your induction generator, in case of an alternator, you can connect supply of alternator directly to the grid without any interfacing medium. That's why when compared with your induction generator, alternator is very widely used. Okay, no doubt.